So looking at the group 1 metal fluorides and applying an equal energy source to them, which one's going to break first? Well, you know what? It's the potassium fluoride. That has the lowest lattice energy and therefore requires the least energy to break the ions apart. Now, why is that? Well, the potassium ion is the biggest of the group 1 ions there, so that positive charge is spread out over a greater surface area, so the potassium ion is less attractive. What about magnesium and calcium fluoride? Well, we would expect those to have a higher lattice energy. After all, they have a +2 charge on that ion. And that's going to give an increased charge density, more attractiveness to those fluoride ions. And just as a point of reference, don't worry about the fact there are 2 fluoride ions, whereas before there was only 1. That doesn't play any part in this. So consider tungsten carbide. This is just a pair of the ions. It's actually a huge crystal, supposedly. Why does this have one of the highest lattice energies out there? Well, if we consider this equation, it might help to illuminate that. It's not IB, but I find it helpful. Q1 and Q2 are the charges on the ions. So as the ionic charges increase, so does the lattice energy. Of course, there's more electrostatic attraction between the ions. And as the distance r between the nuclei increase, well, that means the ions are essentially bigger and bigger and bigger. Charge density is reduced, and of course the lattice energy is therefore going to go down. So even though the carbide ion is huge, that -4 charge really is important here. So silver fluoride, silver bromide, which has the lowest lattice energy. Silver bromide, that large bromide ion, is less attractive than the fluoride ion. And which of these 3 has the highest lattice energy? Yep, magnesium oxide. The ions there are small and have a high charge relative to the others. And we're done.